Well, in the process of taking this guy apart to recap it, I pulled this board out here. It's the main board for the channel that had the worst ripple. You can see where it came from on that side. You literally had to take out tons of screws on the back, just all these screws, some on the bottom. I thought this was kind of a nice touch. This little wire tie here is actually threaded with metal threads. Pretty slick. So get this guy out. It's pretty easy to take out once you figure out how, and generally in good shape. Past transistors here. None of the caps tested horribly. Some were maybe a little out of spec on ESR, so I will end up replacing some of them. But I gotta tell you about a nice mistake I made here. Coming in, I was measuring, the power's off here now, I was measuring right here. And that is about 355 volts on this big cap. That's the filter cap for the main power supply output, and before it's regulated. And I touched this nice long probe to here and here simultaneously, shorting 355 to a negative 5 volt rail, which goes over to the meter. So the meter is blown out. You see that was the reading I had there, 5.19. It definitely burned out that Zener right there. And I'm still troubleshooting to see if I can figure out if I killed this chip, which I think is a chip that does the metering as well as drives the LEDs, or if I've also killed maybe one or these transistors here. So that's where I am now. I got the display board out. Here's a quick sloppy replacement of this Zener in here, which did give me the correct voltage, but I need to go through it further. So I think I'm going to pull out the other side and start measuring voltages on the other side and kind of do a comparison. That piece of paper was just to prevent the circuit board from shorting. So I'm going to pull this guy out and take some readings and compare the two and see what I can figure out. Well, after disassembling both display units, this is the front of the unit. The LEDs shine through those red filters there. I took both sides apart and I took a bunch of readings off each side, and I really think it's this big Pt2 package. It's an Intercell ICL 7107 CJL. It's a pretty common meter chip, 3.5 digit meter chip. So I'm going to get actually a couple of those. I'm going to make sure I have a 40-pin socket too, because I'll put a socket in case I ever do something stupid like this again. And we'll get one of those ordered and put in. That might take a while. I'm probably going to get one off eBay from China. Might be counterfeit. You never know when you buy chips off eBay, but they are so much cheaper. And well, I don't know. This is a good piece of test equipment, so maybe I'll just get one from Mouser. All right, we'll be back. So after my multimeter shorting extravaganza, I determined that this diode was a Zener diode, was blown out, and indeed destroyed the old chip there, the IC7107. So I desoldered the old one, put a socket in, got a new one, put it in. But that let me study this chip and learn about how it works. And basically I determined that they have it set up so that its update rate on the meter here is kind of slow. It's slower than I would like when you when you adjust the knobs up and down to change the voltage, it lags, and that makes it real easy to overshoot or undershoot the voltage that you're after. So what I'm going to do is I'm going to pull out this capacitor here and this resistor. I think it is our 205. I believe I need to double check the schematic, and replace those with some smaller values that will cause the update rate to increase on the meter. And then I'll compare this meter with the other one that I won't modify, and we'll see how that goes. Okay, just to take a look at the schematic to see what we replaced there. This is the IC. It's an A to D converter, IC L7107, if I recall. And in the data sheet, you can find that right in here, between these two pins, this capacitor and this resistor are used to control the frequency of the oscillator in the processor. Well, in the A to D converter, which is also a type of processor, I suppose. The faster this oscillates, the faster the update rate of the A to D converter and of the meter. And Lambda chose a 100 picofarad and 200 K resistor, 100 picofarad capacitor. That makes for a pretty slow update rate. I think it's I had calculated it out, but that was many weeks ago. I've been kind of bogged down with some other stuff lately. I think it's maybe once every second or two. So let's take a look at the update rate here. So you can see I changed the voltage, and it takes a long time for it to update. And that could very easily cause you to overshoot. So say I want to set this to 30 volts. I start going, whoa, I'm past, see? So that's kind of an issue. So what I did was, per the data sheet for this chip, which I will try to link in down below, I changed this this capacitor to roughly 50 picofarad. I think it's 51, and this resistor to, I think it was 50K. And those are the minimum recommended values for, or rather on the data sheet. And that provides a substantially faster update rate. So we went from RC combo there of 200 and 100 to 50 and 50. So that's a pretty substantial increase. So let's take a look here. So now I turn it, and it updates pretty much right as I'm turning it. There's no real delay. Now the only reason that I can think that they may have chosen those values was just so that if you end up between two, like you see here, it doesn't oscillate so quickly. You know, kind of trigger back and forth. But you know what? That really doesn't bother me at all. To be honest, I can always just tweak the 10-turn pot until it holds still. So I'm pretty happy with this change. I don't want to take this voltage up too high. But you can see it's significantly faster than the update here. So pretty excited about that. And honestly, I wouldn't have studied up on this chip if I hadn't caused the short and blown it out. So I learned something in the process. Apparently this is a real common A to D converter chip used in meters. That's pretty much what it's designed for. And now that I'm familiar with it, I see it in all kinds of designs. So learn something new by my mistake. Always a good thing. Now I still have to replace the capacitors, which I hate to admit I haven't even ordered yet. As soon as I caused this problem, I just wanted to resolve it and make sure I could get things going. So I'll place an order for some caps, and then we'll go from there. So it turns out maybe the Lambda engineers weren't so dumb after all. They did indeed pick those values to prevent the oscillation of the meter readings. As you can see here, it's going between or among three different values here, 163, 164, and 165. And it's rock solid here, pretty much at 166. So I think I'm going to swap out the resistor. Like I said, I took the capacitor from 100 picos to 50 or 60 pico, I think is what they actually measured, and I took the resistor from 200K to 50K. So I think I'm going to maybe try I don't know, somewhere in the range of 86K resistor or something like that. See how that works out. Okay, I swapped out the resistor on this channel with an 82K resistor, and it might be a tiny bit better. It is a hint slower, of course, but it still seems to have quite a bit of variation in it. And it's possible because the right side, which still has the 50K, can get pretty stable, right? And it never seems to vary more than 1 volt, whereas this guy varies 2 volts frequently. So I'm wondering if it isn't the cheap IC70-107 chip that I bought off eBay from China that I put in this side. Either the tolerances are different or it's just junk. So I think what I'll do is I'll replace the capacitors that I was planning on doing, and we'll see how stable this is. And we might just have to go back closer to the original values to try to smooth this out and see how that works out. Otherwise, maybe buy a real chip off Mouser or something rather than eBay, but they were, of course, significantly cheaper from China. I'm guessing they're counterfeit, but I don't know. So we'll give that a shot in the next video. Thanks.